A corroded bronze gear recovered from a shipwreck holds a 2,000-year-old secret. We are about to uncover 25 ancient discoveries that reveal the origins of scientific thinking, a journey that will forever change how you see our intellectual heritage. You will see how the roots of modern physics, astronomy, and medicine stretch back into a past we are only beginning to understand. How did a culture with no telescopes create an analog computer to predict the cosmos? What mysterious device might have generated an electric current centuries before its official discovery? By the end, you will witness a global tapestry of innovation that proves the drive to experiment and explain is as old as humanity itself. What do you believe is our greatest inheritance from the ancient thinkers? That diver pulled a rusted puzzle from the seabed, a lump of metal and wood that would baffle researchers for generations. For decades, the object sat quietly in a museum, labeled as a curiosity. Then in the 1950s, a historian of science named J. Price began to look closer. Using the latest tools of his time, including early X-ray imaging, he started to peer inside the corroded mass. What he saw was astonishing. Delicate bronze gears, some with intricate triangular teeth, were interlocked in a complex system. This was no simple statue fragment or navigational tool. It was a machine. A machine built around 100 years before the Common Era in ancient Greece. The mechanism, as it came to be known, is an analog computer of staggering sophistication. Its purpose was to model the cosmos. By turning a hand crank, an operator could see the predicted positions of the sun, the moon, and the 5 planets known to the Greeks. It could forecast solar and lunar eclipses with remarkable accuracy. It even tracked the 4-year cycle of the Olympic Games. The real shock for modern engineers was the presence of a specific component called a differential gear. This is a complex arrangement of gears that calculates differences in motion, and it was a technology historians believed was not invented until the 16th century, some 1,700 years later. Yet here it was, in a device from classical antiquity. This tells us something profound. The mechanism was not a lucky guess or a one-off marvel. It was the physical product of a deep, established tradition. Its creation required generations of precise astronomical observation, advanced mathematical theory to translate those observations into gear ratios, and a masterful level of craftsmanship to build it. This was science made solid, a working model of the universe constructed from bronze and ambition. It forces us to ask a difficult question. If this level of technical knowledge existed, what else was known, and how much of it was lost when that ship sank? The mechanism is our first, stunning clue that the origins of computational thinking are far older and more advanced than we ever dared to believe. The gears of the mechanism represent a pinnacle of mechanical precision, but what about a discovery that seems to channel an invisible force? In the 1930s, among the ruins of a village near what is now Baghdad, archaeologists uncovered a collection of simple clay jars that would ignite a modern scientific mystery. Each jar, about the size of a man's hand, held a strange assembly. A copper cylinder was soldered shut at the bottom and suspended inside the jar. Down its center ran an iron rod, and the entire top was sealed with a thick plug of asphalt, a naturally occurring tar. To any modern eye familiar with basic electronics, the setup is uncanny. It looks exactly like a primitive battery. These artifacts are dated to a period spanning from roughly 250 years before the Common Era to 650 years after, a time of the Parthian and later Sasanian empires. The immediate question is obvious. What was its purpose? The objects themselves offer no inscription, no manual, so researchers did what the ancients might have done. They experimented, filling a replica jar with an acidic liquid like vinegar or grape juice, which would have been readily available. They completed a circuit between the copper cylinder and the iron rod. The result was a low but measurable electric current, around 1 volt. It is not enough to power a light, but it is a genuine, reproducible spark. This is where the debate truly begins. Without a written record, we are left to infer function from possibility. One compelling theory suggests electroplating, the process of using electricity to bind a thin layer of one metal, like gold, onto the surface of another, like silver. Artisans of the time were masters of gilding, and a small battery could have provided a controlled method for this delicate work. Another idea points to ancient medical practices, where the mild tingling sensation from such a device might have been used for therapeutic purposes, a form of early electrotherapy to soothe aches. The profound implication of the Baghdad Battery is not that it powered an ancient city. It is far more subtle and revolutionary. It suggests a culture engaging in what we might call proto-experimentation. Someone, at some point, observed a chemical reaction between different metals and a common liquid, noticed a strange sensation or perhaps a subtle plating effect, and then deliberately engineered a device to reproduce and harness that phenomenon. This is not full-blown theory. It is the essential first step of all science, careful observation followed by practical application. The jar stands as a quiet challenge to our neat historical timelines, a whisper that the basic principles of electrochemistry were being tinkered with long before, and Volta gave them names. It pushes us to look at other ancient wonders not as magic, but as potential evidence of a hands-on, trial-and-error approach to the natural world. Deep within the stone walls of the Temple of Hathor, a particular carving has sparked a debate that illuminates a different kind of ancient thinking. The bas-relief shows a strange scene. A large, bulb-like shape rests on a stand. Inside it, a serpent stretches along its length. A cable seems to connect the bulb to a box held by a kneeling figure, while a two-armed symbol, reminiscent of a pillar, stands nearby. To a modern viewer, the resemblance to a primitive light bulb is startling. Could this be evidence of ancient electrical knowledge, a literal depiction of a lost technology? Mainstream archaeology offers a different, symbolic interpretation. Experts identify the bulb as a lotus flower, a sacred symbol of creation and rebirth. The serpent inside represents the god Hapi, associated with the annual flooding of the Nile, a life-giving force. The entire tableau is a part of a well-documented creation myth, carved in a sacred space meant for ritual, not a technical manual. So why does the light bulb interpretation persist so powerfully? This is where the carving becomes a fascinating case study in how we interpret the past. It pushes us to ask a crucial question. Are we seeing what was actually there, or are we projecting our own world onto theirs? The hypothesis, while not supported by physical evidence like wires or batteries found at the site, forces a deeper discussion about how ancient cultures conceptualized invisible forces. They understood the power of the sun, the mystery of bioluminescence, the terrifying energy of lightning. Their science was not separate from their spirituality. It was woven into it. A symbol like this could represent the abstract concept of illumination, of divine energy made manifest, of harnessing a cosmic power for ceremonial purposes. The relief, whether a misunderstood flower or a speculative blueprint, ultimately represents the universal human drive to explain and control the unseen forces of the world. It reminds us that the line between myth and proto-science was often beautifully blurred. The real discovery here is not a working light bulb, but the insight into how a civilization used the language of symbol to grapple with the fundamental ideas of energy and creation, concepts that our own science would later define in very different terms. Centuries before the Baghdad jar sparked its quiet current, another force was being harnessed in a library far to the west. In the great scholarly hub of Alexandria, an inventor named Hero documented a device of elegant simplicity and profound implication. He called it an. Picture a hollow metal sphere mounted between two pipes that connect it to a sealed pot of water below. When a fire is lit beneath the pot, the water boils. Steam rises through the pipes into the sphere, where it escapes from two bent nozzles pointing in opposite directions. The result is not a quiet hiss, but a powerful, whirling spectacle. The sphere spins, faster and faster, propelled by the jets of escaping steam. This was not magic. It was a clear, working demonstration of a fundamental physical principle, action and reaction, the very force that would one day launch rockets into space. Hero and his peers understood they were witnessing the transformation of heat into motion, a core concept of thermodynamics. Yet there remained what historians call a temple wonder, a philosophical toy displayed to inspire awe and curiosity about nature's secrets. It was not connected to a wheel, a pump, or a loom. Why would such a brilliant insight not be put to practical work? The answer lies in the world that surrounded the invention. The economy of the ancient Mediterranean was built on abundant human and animal labor, readily available and understood. There was no pressing social or economic drive to replace it with complex, fuel-hungry machinery. There was a solution in search of a problem that its society did not yet feel, but to dismiss it as a mere toy is to miss its staggering significance. Hero compiled his work, including designs for automated temple doors, singing mechanical birds, and even a primitive vending machine, in a volume called This book is a testament to systematic engineering thinking. It shows a culture actively playing with the laws of geometry and physics, not just contemplating them in the abstract, but bending them to human will for the purposes of ritual, entertainment, and pure intellectual delight. The proves the knowledge was there, simmering like the water in its boiler. It would take a different world, one facing different pressures and possessing different ambitions, to finally channel that steam into an engine that would change everything. The real question it leaves us with is not about levers and boilers, but about context. What ideas do we play with today that a future civilization might look back on and wonder why we never truly used them? A sphere spinning on steam reveals a playful mastery of physics. But what happens when an artifact seems to defy time itself? In the winter of 1961, 3 men hunting for geodes in the mountains of California cracked open what they thought was a particularly promising stone nodule. Inside, they did not find the expected crystalline cavity. Instead, they discovered a hard cylinder of clay with a 2 mm metal shaft running through its center, all encased within the geode's layered shell. To their eyes, it looked uncannily like a modern spark plug encased in stone. Dubbed the artifact, its story quickly spiraled. The geode was initially claimed to be 500,000 years old, a date that, if true, would place a piece of 20th century technology deep in the Pleistocene epoch. How could this be possible? The artifact became a flagship example of what enthusiasts call an out-of-place artifact, an OOP art, an object that seems to exist outside of established historical timelines, challenging everything we think we know. The mystery, however, began to unravel under scrutiny. Independent researchers, including a trained geologist, examined the object and proposed a far more mundane explanation. The inner core was not a spark plug ceramic insulator, but a hardened lump of iron concretion, a natural process where minerals cement around a metal object. The outer shell was not a 500,000-year-old geode, but a case of hardpan, a dense mineral deposit that can form in decades, not. The most likely candidate for the original object was indeed a 1920s-era champion spark plug, perhaps lost by a miner or a rancher, which then became rapidly encased by local minerals. The artifact teaches in scientific thinking. It is not a story of a lost advanced civilization, but a case study in how we investigate anomalies. The initial excitement highlights a very human tendency, pattern recognition. We see a familiar shape in an unfamiliar context, and our minds leap to an extraordinary conclusion. The subsequent investigation demonstrates the essential tools of reason. First, there is razor, the principle that the simplest explanation with the fewest assumptions is often correct. A spark plug from the recent past encased by natural processes is infinitely more probable than a temporal paradox. Second, it underscores the absolute importance of context and rigorous verification, especially in dating. An object is only as old as the layer it is found in, and that layer must be studied with care. Finally, the case warns of confirmation bias, the subconscious desire to interpret new evidence in a way that confirms what we already wish to be true. The true value of the artifact lies not in what it was, but in the questions it forces us to ask. How do we responsibly investigate a genuine mystery without letting wonder override our critical faculties? The answer is to embrace the role of the detective, not the believer. We must follow the evidence, even when it leads to a conclusion less spectacular than we hoped. For in that disciplined pursuit, we honor the real scientific process, a slow and careful sifting of fact from fascination, which has always been our most reliable guide through the mysteries of the past. The disciplined sifting of fact from fascination defines true inquiry, but what of a document that resists all sifting? In a library in New Haven, Connecticut, rests a book that has consumed the minds for over a century, yet gives up nothing. The manuscript is a 240-page codex from the 15th century, bound in vellum and filled from edge to edge with a script that belongs to no known language. Its pages bloom with illustrations of plants that have never grown on Earth, their roots and leaves twisting in impossible configurations. They show celestial charts with unfamiliar constellations and intricate networks of pipes connecting pools where nude women bathe. Since its rediscovery by a Polish book dealer in 1912, this volume has been a black hole for understanding, absorbing every attempt at decryption and yielding no light. Professional code breakers from both world wars, modern linguists with supercomputers, and armies of devoted amateurs have all applied their skills. The result is always the same, profound and tantalizing silence. The script shows statistical patterns consistent with a real language, not random gibberish, yet it matches no known cipher or linguistic family on Earth. This leads to a forest of competing theories. Is it an elaborate, centuries-old hoax crafted to fool a wealthy patron? Could it be a record of a lost natural language, perhaps from a community that left no other trace? Or is it a highly personal constructed cipher, a secret diary of observations meant only for the eyes of its creator? The manuscript's vary is its most important lesson. It forces us to confront the architecture of knowledge itself. Look at its sections, they are clearly organized. There is a herbal segment, with each strange plant given a full page and paragraphs of text, mimicking the medicinal herbals of its time. There is an astronomical section with fold-out charts of the stars. There is a biological section with those intricate piping systems, possibly representing early ideas about human physiology or the flow of vital energies. This is not chaos. It is a systematic attempt to categorize the natural world, but within a framework of understanding that is completely alien to us. The manuscript embodies the ancient and universal practice of encoding knowledge, whether for protection, for ritual, or simply as an intellectual fortress. It demonstrates that the act of organizing information, of creating a system to contain one's observations of plants, stars, and the human body, is itself a foundational scientific endeavor. The creator was doing what all early natural philosophers did, observing, classifying, and recording. We simply cannot read the rules of their system. So what can an unreadable book teach us? It teaches humility. It is a stark reminder that the history of science is not a straight line of accumulating facts we now understand. It is a landscape dotted with isolated peaks of insight, systems of thought that rose, flourished in a particular mind or culture, and then vanished, leaving behind only cryptic monuments like this one. The manuscript is not a locked door waiting for a key. It is a mirror, reflecting back at us the limits of our own perception and the enduring, haunting allure of a mind from the past we may never truly meet. A book no one can read speaks of knowledge we cannot access, but a map from the same era offers a different kind of mystery, one written in coastlines and annotations. In the year 1513, Ottoman admiral and cartographer put the finishing touches on a world map, a portion of which survives today in the palace. At first glance, it is a beautiful artifact of its age, showing the familiar contours of Europe and Africa. But look to the west, and the map reveals something astonishing. The eastern coastline of South America is rendered with a precision that seems impossible for European maps of that early date. Even more controversially, a landmass at the bottom of the chart appears to some to depict the northern coast of Antarctica, a continent that would not be officially discovered for another 300 years, and shown here curiously free of ice. This interpretation has fueled countless speculative theories about lost civilizations or advanced prehistoric knowledge. Mainstream scholarship, however, points to a more grounded, yet no less brilliant explanation found in the map's own margins. Wrote extensive notes directly on the parchment, and in them he credits his sources. He lists some 20 different charts and Portolan maps, including those from Arab, Portuguese, Spanish, and even ancient Greek sources. He specifically mentions using a map drawn during the time of Alexander the Great. The admiral was not a clairvoyant. He was a master synthesizer, a scholar of the sea. His map is not a snapshot from a satellite, but a layered document, a patchwork quilt of empirical data stitched together from generations of sailors who had actually been there. The controversial southern land is far more likely a misinterpretation, perhaps a composite of the southern coasts of South America or a legendary southern continent that had been part of mapmakers' lore for centuries. The true genius of the map lies not in its potential anomalies, but in its explicit methodology. It is a physical record of the scientific process applied to geography. Cross-referenced his sources, noted discrepancies, and made informed choices to create the most coherent model possible from the conflicting information he had. His annotations are like a researcher's footnotes, giving credit and providing context. This shows a culture engaged in systematic knowledge accumulation, where new data from Portuguese explorers rounding Africa was integrated with older Arab trading charts and classical geographical concepts. It exemplifies how the world was pieced together, not in a flash of revelation, but through the slow, careful work of comparison and synthesis. So how did those ancient mariners, whose charts studied, achieve such accuracy without satellites or chronometers? They relied on a profound intimacy with their environment. They tracked the stars with simple cross staffs, read ocean swells and cloud formations, observed the migratory patterns of birds, and recorded wind directions with meticulous care. Their science was one of acute observation and lived experience, translated into practical lines on a sheepskin chart. The map is a testament to that accumulated wisdom, a bridge between the speculative geographies of antiquity and the empirically driven cartography of the Age of Discovery. It reminds us that the most accurate model of the world often begins not with a single stroke of genius, but with the humble, essential act of comparing notes. The precision of a map drawn from countless voyages finds a startling parallel not on parchment, but in the very earth itself. High on the arid plains of southern Peru, a desert plateau holds one of archaeology's most breathtaking enigmas. Across nearly 200 square miles, the people, between 2,000 and 1,500 years ago, etched a gallery of colossal art into the landscape. They did this not by piling stones, but by removing the dark, sun-baked surface pebbles to reveal the lighter-colored soil beneath, creating stark, contrasting lines. The resulting depict a hummingbird with wings outstretched, a spider with perfectly proportioned legs, a monkey with a spiraling tail, and vast geometric shapes like trapezoids and spirals that stretch for miles. Their scale is so immense, their form so coherent, that they are truly comprehensible only from the air, a fact that has fueled endless speculation about ancient astronauts or lost technologies. The reality of their creation, however, is a testament to a different kind of genius, one grounded in practical, communal science. How do you draw a straight line for 5 miles without a laser, or scale up the intricate curve of a bird's beak to a size larger than a football field? Archaeologists, through experiment and observation, have demonstrated that it was likely achieved with elegant simplicity. Teams of workers could have used a central hub and long ropes, like a giant compass, to create perfect circles and arcs. For straight lines and complex shapes, they could have constructed a scaled-down model on a small plot, then used a grid system of stakes and cords to transfer the design, point by painstaking point, onto the monumental canvas of the desert. This process required a sophisticated, shared understanding of geometry, proportion, and measurement. It was applied mathematics on a territorial scale. The purpose behind this immense effort remains gently shrouded in time. Leading theories suggest the lines served as sacred pathways for ceremonial processions, where communities walked the figures in ritual acts. Others see them as a vast astronomical calendar, with certain lines aligning with the solstice sun or important star clusters on the horizon, connecting the people to cosmic cycles. Perhaps they were offerings to deities believed to dwell in the sky, prayers for water etched into the desperately dry land. What is undeniable is the project's sheer logistical magnitude. Organizing and sustaining the labor to create and maintain these lines over centuries speaks to a highly coordinated society with shared goals and specialized knowledge. The lines blur the line we often draw between ritual and science, between art and engineering. They show that the drive to measure, to plan, to execute a grand design upon the world is not confined to laboratories or workshops. It can be an act of communal devotion, where geometry becomes a language for speaking to the gods, and the desert itself becomes a permanent record of a culture's ability to see a pattern in their mind's eye and imprint it upon the earth. This monumental achievement forces us to ask, what other expressions of precise thinking might we be overlooking? Simply because they were crafted for a purpose, we no longer fully understand the monumental geometry of the desert finds its counterpart in a single, silent column of metal half a world away. In the courtyard of the Islam Mosque in Delhi stands an object of profound industrial mystery, the Iron Pillar. It rises over 7 meters or 23 feet and has done so for more than 1,600 years. What makes it a marvel is not its height, but its condition. In a region with distinct wet and dry seasons, exposed to monsoon rains and urban pollution for centuries, this massive iron structure shows almost no sign of the rust that should have consumed it long ago. Forged in the 4th century, during the brilliant Gupta Empire, the pillar's endurance is not a lucky accident. It is the signature of a metallurgical science far ahead of its time. Modern analysis has revealed its secrets. The iron is of exceptional purity, with a very low sulfur content, a testament to the skill of the smelters who processed the ore. More crucially, the metal has a high percentage of phosphorus. This unusual composition, combined with the local climate, encourages the formation of a thin, stable, and incredibly protective film on the surface, a passive layer that shields the iron beneath from further attack. This is not a concept ancient smiths would have articulated in chemical terms, but it was a result they clearly understood how to achieve. The creation of such a pillar was an epic feat of logistics and craft. It likely required a series of small furnaces operating in concert, each producing a bloom of hot iron that was then hammer-welded together under immense heat, a process repeated until the entire column was formed. This indicates generations of accumulated knowledge, a tradition of trial, observation, and refinement passed from master to apprentice. They learned through practice that certain ores, processed in certain ways, yielded a metal that lasted. They solved the eternal engineering problem of decay not with abstract theory, but with the soot-covered wisdom of the forge. The pillar stands as a monument to a solution-oriented, empirical mindset. It asks us to look beyond temples and texts for evidence of ancient science, and to see it instead in the very materials that shaped their world. In its uncorrupted surface, we see 1,000 years of questions asked at the anvil and answers hardened into iron. That silent pillar of iron demonstrates mastery over materials, but another artifact seems to reach for the very sky. Within a tomb at Saqqara, resting for over 2,000 years, lay a small object carved from sycamore wood. At first glance, it is a simple bird figurine, a common funerary offering. Yet its proportions are unusual, and its most striking feature is a tail that stands completely vertical, not horizontal like a bird's tail feathers, but precisely like the vertical stabilizer on the tail of a modern airplane. This is the Saqqara Bird. To most Egyptologists, it is a ceremonial object, perhaps a child's toy or a model of a falcon representing the god Horus. Its purpose was likely symbolic, not aerodynamic. But its unique shape has prompted a fascinating question from a modern perspective. Could its form, even unintentionally, hold principles of flight? In the 1990s, a specialist in aerodynamics examined a replica. He noted that the wings are indeed airfoil-shaped, curved in a way that could generate lift. That vertical tail, he argued, could provide lateral stability, preventing a glider from spinning out of control. When tested as a model glider, with a small horizontal stabilizer added to the tail that might have been lost over time, some replicas have reportedly shown surprisingly stable flight characteristics. The debate is not about whether ancient Egyptians had airplanes. They did not. The profound implication lies in the process of observation and mimicry. Craftsmen spent lifetimes observing the natural world with an artist's eye and an engineer's hands. They saw how a bird's wing cuts the air, how its tail steers its descent. In shaping this ritual object, they may have intuitively captured aerodynamic truths they had no language to describe. The Saqqara bird symbolizes the timeless human dream of flight, a dream pursued in myth with winged chariots and in careful study of soaring raptors. It represents a moment where art, ritual, and the subconscious absorption of natural law intersect. This small wooden model challenges us to reconsider other ancient objects not just for their cultural purpose, but for the embedded knowledge they might accidentally preserve. It asks if the seeds of complex engineering principles can be found scattered in the artifacts of daily life and sacred practice, waiting centuries for a new way of seeing to recognize the intuition hidden within their form. A wooden bird's silent intuition about flight stands in stark contrast to a weapon that roared across the sea. For the Byzantine Empire, survival often depended on a terrifying secret, a liquid flame that could not be extinguished by water. This was Greek fire, the ancient world's most closely guarded technological edge. Imagine the scene from a besieging fleet's perspective. A Byzantine warship turns, and from its prow, a bronze tube projects not a bolt or a stone, but a roaring jet of fire that arcs across the waves. It strikes an enemy vessel, and the sea itself seems to ignite, creating a hellish inferno that clings to wood and flesh alike. Water only spread the burning substance. For over 7 centuries, this weapon helped protect Constantinople from naval assaults, its psychological impact as potent as its physical destruction. The exact formula was a state secret of the highest order, known only to a few, perhaps even within a single family. Historians, piecing together fragmented accounts, suggest its base was likely crude petroleum, similar to modern, drawn from natural surface wells around the Black Sea. To this, compounds like quicklime, which ignites on contact with water, sulfur, or saltpeter may have been added, creating a thickened, sticky concoction. The delivery system was as ingenious as the chemical mix. It was pumped through pressurized bronze siphons, allowing operators to aim the fiery stream with devastating precision. This was not a lucky accident or a simple torch. It was the result of deliberate, systematic research and development, a military research project funded by the state. Teams of alchemists and engineers would have experimented for years, testing different ratios and delivery mechanisms, observing results, and refining their terrible recipe through rigorous trial and error. The knowledge was then protected with a secrecy we would associate with modern classified weapons programs, a supreme intellectual property that defined an empire's security. Greek fire forces us to confront a timeless ethical dimension of discovery. Here was a monumental achievement in applied chemistry and mechanical engineering, born from the urgent need for defense, yet whose sole purpose was immense destruction. It exemplifies the dual-use nature of technology, a concept as relevant today as it was in the 7th century. The same empirical mindset that sought to understand the properties of petroleum could be channeled toward creation or devastation. This ancient weapon asks us to reflect on the path of innovation itself. How do societies navigate the line between safeguarding their people and unleashing tools of terrible power? The lost formula of Greek fire is a reminder that some of history's most advanced scientific thinking was often forged not in peace, but in the desperate, brilliant heat of conflict. Yet a far more accessible tool was quietly shaping the foundations of global trade and thought. The abacus, in its many forms, was humanity's first universal computational engine. Its design is a study in elegant simplicity, a frame holding rods or wires along which beads can slide. In ancient Mesopotamia, a dust abacus used lines drawn in sand. In Rome, it was a bronze tablet with grooves. In China, they evolved with a sophisticated upper and lower deck of beads. Despite these variations, the core principle remained brilliantly consistent. Each bead represented a specific value based on its position. By moving them, a user could perform complex arithmetic, embodying the revolutionary concept of place value long before it was formalized in written numerals. This was not a passive tool. It required active engagement, a tactile dialogue between hand and mind that made abstract numbers physically real. Merchants used it to calculate profits and tariffs across bustling markets from the Silk Road to the Roman Forum. Engineers relied on it to tally materials for aqueducts and temples. Astronomers employed it to track celestial cycles. The abacus externalized calculation, taking the burden of memory and procedure off the individual's mental scratchpad and placing it into a shared, standardized system. Anyone trained on the device would arrive at the same answer for the same problem, a crucial step toward reproducible, objective results. Its endurance for over speaks to a profound truth about our relationship with technology. The abacus did not compute on its own, it augmented the human mind. It extended our innate cognitive capabilities, allowing us to manipulate quantities far beyond what we could hold in our heads. In this sense, it is a direct philosophical ancestor to every computer that followed. The silicon chip in your phone is simply a vastly faster, automated version of the same fundamental idea, a structured system for processing symbolic information according to set rules. The abacus represents the moment we began to build machines not just for physical labor, but for the labor of thought itself. It reminds us that the digital age did not begin with vacuum tubes, but with beads clicking on rods, a sound that once orchestrated the mathematics of empires. But that universal tool for calculation needed a home for the ideas it served. On a bustling harbor in the ancient Mediterranean, a king had a vision far grander than any single invention. He dreamed of a sanctuary not for a god, but for knowledge itself. The Library of Alexandria was founded in the 3rd century before the Common Era by Ptolemy I, a general of Alexander the Great. Its stated mission was audacious, to collect every single book in the world. Agents were dispatched across kingdoms with royal funds to purchase or borrow scrolls from Athens to India. Every ship docking in Alexandria's legendary port was searched, and any scrolls found were confiscated by scribes with meticulous care, and the copies returned to the owners while the originals stayed in the library's vast collections. This was not mere hoarding. It was the first systematic attempt to create a complete, centralized database of human thought. The library became a living ecosystem of the mind. Within its halls and adjacent research institute, the scholars were provided stipends, housing, and most importantly, access to each other's work. Here, Euclid organized the scattered principles of geometry into his definitive elements, a textbook of logical proofs that would be used for 2,000 years. Here, Eratosthenes, by comparing shadow lengths in 2 distant cities, calculated the circumference of the Earth with astonishing accuracy. Here, Archimedes, visiting from, would have debated mechanics and mathematics with his peers. This environment institutionalized the very practices that define modern science. Scholars translated texts from Egyptian, Babylonian, and Persian into Greek, creating a common language for scholarship. They wrote commentaries criticizing and building upon earlier works, engaging in a form of ancient peer review. The library's existence declared that knowledge was not the property of a single sage or a secret priestly caste. It was a collaborative, cumulative project. Its tragic and gradual loss, through a series of fires and conflicts over centuries, stands as one of history's most poignant lessons in fragility. The dispersal and burning of its scrolls did not just destroy objects, it severed countless threads in the web of understanding, setting entire fields of inquiry back for generations. The true legacy of the Library of Alexandria, however, is not its tragic end, but its revolutionary beginning. It established the ideal that progress depends on a shared space, both physical and intellectual, where ideas can be gathered, compared, challenged, and synthesized. In a world before digital networks, it was the original internet, a hub where the signal of human curiosity was amplified. This ancient institution asks us a pressing modern question. In an age of information overload and fragmented communication, how do we rebuild that spirit of a shared, reliable repository? How do we foster the kind of open, structured dialogue that turns a collection of facts into a living, advancing conversation? The library's story is a powerful reminder that the most important discovery of all may be the system for making discoveries together. That dream of a universal library shows our drive to preserve knowledge. But what if entire chapters of our story were lost long before any scribe could write them down? The idea of a great civilization, advanced and wise, swallowed by the sea, is one of humanity's oldest and most haunting stories. From Plato's detailed account of Atlantis to the countless flood myths found on every inhabited continent, these narratives speak to a deep, shared intuition. They are given tantalizing shape by artifacts like the map, with its seemingly impossible coastlines, or the discovery of submerged structures off coasts like Japan or India. Together, they fuel a compelling question: could there be a kernel of historical truth behind the legend of a lost, scientifically advanced world? Mainstream archaeology, grounded in the physical evidence we can dig up and date, finds no support for a global, technologically sophisticated civilization in the remote past. There are no layers of ancient plastic, no gears from a forgotten industrial age, no sudden, worldwide leap in material culture. The progress we see in the archaeological record is local, gradual, and beautifully human in its scale. So why does the idea of Atlantis, or its many cousins, remain so powerfully alive? The answer lies not in hidden ruins, but in how we process the past and our own fragility. These stories serve as powerful metaphors. They help explain very real phenomena that ancient peoples witnessed but could not fully understand. Consider the end of the last ice age, around 12,000 years ago. As glaciers melted, global sea levels rose by over 100 meters, drowning vast coastal plains where generations of people likely lived. To those who survived, watching the relentless ocean claim their homes over generations, it would have seemed like the gods had unleashed a global deluge. This was not a myth, but a lived, catastrophic reality passed down as oral history for thousands of years. Similarly, the discovery of mammoth bones or giant seashells far inland could easily be interpreted as the remains of a primeval world of giants and monsters. The stories that grew from these seeds were a form of early science, attempts to make sense of a landscape filled with puzzling clues. Examining these theories critically teaches us to separate geological memory from literal history. It shows the difference between a myth, which carries cultural truth and meaning, and a historical record, which requires verifiable evidence. The persistent appeal of lost civilizations also reflects a profound psychological pattern: the awareness of cycles. Almost every culture has a concept of golden ages and dark ages, of creation and destruction. This intuition recognizes that knowledge is fragile, that libraries burn, that languages fade, and that even the mightiest cities can be reclaimed by forest or sea. In a way, these stories are ancient warnings about the impermanence of human achievement. They connect directly to our modern anxieties about climate change, digital decay, and how we preserve our own civilization's knowledge for the future. So do these tales contain kernels of truth? Absolutely, but not of forgotten superscience. Their truth is about human experience, the trauma of natural disasters, the resilience of communities who rebuilt, and the enduring need to find meaning in the scars left upon the world. They remind us that the greatest discovery we can make about the past is often about understanding the storytellers themselves, and why they needed to speak of a world that vanished beneath the waves. A world reclaimed by the sea speaks of impermanence, but the human body presents a more immediate and intimate frontier. Among the most direct evidence of ancient scientific thinking lies not in grand temples, but in small, precise objects designed to heal, or at least to intervene. In museum cases across the world, you can find them: Roman bronze scalpels with blades still sharp, intricate trephination kits from ancient Peru with obsidian drills, and delicate bronze probes and forceps from Greece and India. These are not crude, multi-purpose tools. Each has a specific, recognizable design, honed for a particular task, a sign of standardized medical practice and a deep, if incomplete, understanding of anatomy. The Greek physician Galen, working in the 2nd century, famously systematized medical knowledge through observation and dissection, primarily on animals like pigs and apes. His detailed writings on the nervous system, the pulse, and the functions of organs, while mixed with the prevailing theory of the four humors, were based on methodical examination. This created a foundational bridge between philosophical speculation about the body and its physical, observable reality. The tools themselves tell a story of pragmatic problem-solving. A Roman bone lever was engineered to fit into a fracture and apply precise pressure to set a broken limb. Specialized hooks and blunt spatulas were used in cataract couching, a procedure to displace a clouded lens from the field of vision. The very existence of these specialized instruments implies a process of iterative refinement, where earlier, cruder versions were gradually improved upon based on what surgeons observed worked best in practice. This blend of guiding theory, like balancing humors, with hands-on technical skill defines the early scientific approach to medicine. It acknowledged the body as a system that could be studied and, to a limited extent, repaired. This naturally leads to a daunting question. How did they manage the twin horrors of the pre-modern operating theater, agonizing pain and rampant infection, without our modern solutions? Their approaches were a mix of ingenuity and necessity. For pain, surgeons relied on herbal analgesics like opium or mandrake root, applied as drafts or inhaled smokes. They also used physical methods like compression of nerves or even swiftness, the ideal being to complete a procedure like an amputation in under a minute. To combat infection, they employed what they observed worked: cleaning wounds with vinegar or wine, which have mild antiseptic properties, and using honey as a natural antibacterial dressing. While far from foolproof, these methods were not random superstition. They were applied observations from the natural world, tested through grim trial and error. The evolution of these delicate, deadly serious tools demonstrates a quiet courage, a willingness to engage directly with the fragile machinery of life, using the best knowledge and craftsmanship available. It was a science born not in abstraction, but in the urgent, blood-stained reality of human suffering, where every refined scalpel shape represented a hard-won lesson and a hope for relief. Those delicate surgical tools reveal a mind seeking order within the body, but another artifact presents a puzzle of order so complete it becomes a fortress. In the ruins of the Minoan Palace on the island of Crete, an Italian archaeologist unearthed a simple object of baked clay in 1908. It is a disc, roughly the size of a small plate, and on both of its faces, a message spirals inward from the edge to the center, stamped into the clay with 45 distinct pictorial symbols. Flowers and birds, human heads and shields, a cat's head and a ship's oar, all arranged in clear, grouped sequences. This is the disc, and it is utterly alone. Created in the second millennium before the Common Era, it is the earliest known document of printed text in the world, each symbol pressed with a separate seal. Yet the script it uses appears nowhere else, not on any other clay tablet, not on any wall or pot from the entire Minoan civilization. It is a linguistic island, a single burst of symbolic communication from a world we can no longer hear. The mystery begins with the most basic question: which way do you read it? Does the spiral start at the rim and wind in, or begin at the center and unwind outward? The symbols themselves offer no obvious direction. Then what do the groupings mean? Are they words, syllables, or perhaps an entire idea represented by a single stamped image? Scholars have proposed countless theories. It could be a religious hymn to a goddess, a legal code for the palace, a narrative of a royal journey, or even the rules for a sacred board game. Without a parallel text, a stone to provide a key, every attempt at decipherment rests on a foundation of guesswork. This has not stopped the effort, and that effort itself is a lesson in scientific methodology. Decoding the disc requires a fusion of disciplines. Archaeologists provide the context. The disc was found in a temple complex, suggesting a ceremonial purpose. Linguists perform statistical analysis on the symbol sequences, searching for the patterns and repetitions that might denote grammar. Computer scientists apply algorithms to model possible languages. Each new approach narrows the field of possibilities, even if it does not deliver a final answer. The disc's profound silence forces a humbling realization. We have before us a clear, organized system of thought, a deliberate creation that its maker and its intended audience understood perfectly. It is a snapshot of a cognitive world, a way of categorizing and recording information that made complete sense to an ancient mind. And that world is gone. The disc did not evolve into a broader writing system like its contemporary Linear B, which was later deciphered as an early form of Greek. It appears, is used for this one purpose, and then vanishes from the historical record. What does this withhold from us? Perhaps not a specific scientific formula, but something equally valuable, an understanding of how another society structured knowledge itself. Did their symbols for a flower and a bee relate to an early study of botany and pollination? Did the repeated image of a ship signify a unit of measure or a calendar cycle tied to navigation? We cannot know. The disc, therefore, is more than an unsolved code. It is a monument to the fragility of understanding. It reminds us that science and administration are not just about the facts one records, but about the shared mental framework, the invisible language of thought, that makes those facts meaningful. When that framework is lost, even the clearest message becomes a beautiful, impenetrable spiral into silence. The silent mystery of an undeciphered disc speaks of lost frameworks, but one ancient structure stands defiant, its framework proudly on display for all the world to see. In the heart of Rome, the Pantheon's dome creates an open eye to the heavens, a perfect circle of light pouring through its oculus. This vast, unsupported concrete ceiling has not just survived, it has thrived for nearly 2,000 years, through earthquakes, invasions, and the relentless wear of weather. Modern concrete, by stark contrast, often shows signs of decay within decades when exposed to the same elements. For centuries, the longevity of Roman concrete was itself an architectural mystery, a secret locked in the very fabric of their empire. Recent scientific detective work, using advanced tools like electron microscopy, has finally cracked the code. The Romans were master mixologists, and their recipe was deceptively simple. They combined lime with a special volcanic ash called pozzolana, mined from regions like, and they mixed it with seawater. This was no random formula. When seawater percolates through this mixture, it triggers a slow, ongoing chemical reaction. Tiny, plate-like crystals of a rare mineral called aluminum grow within the material's pores. These crystals act as a reinforcing agent, actually strengthening the concrete over centuries and allowing it to self-heal tiny cracks as they form. This process is the opposite of modern concrete, which typically weakens as water infiltrates and rusts its steel reinforcements. The development of this material was almost certainly not a single eureka moment. It was the product of generations of careful, empirical refinement. Roman engineers were brilliant observers of the natural world. They would have seen how certain volcanic soils, when mixed with lime and water, formed a rock-hard cement. They experimented with different ratios, different ash sources, and different mixing techniques, meticulously noting which formulations set fastest, bore the most weight, and lasted the longest in their harbors and aqueducts. This was materials science conducted on a colossal scale, a sustained research and development project that spanned centuries and was funded by an empire that viewed enduring infrastructure as a pillar of its power. The concrete they perfected enabled more than just the pantheon. It built the aqueducts that fed cities, the harbors that sheltered fleets, and the roads that bound a continent together. It was the physical manifestation of Roman order and ambition, which makes its subsequent loss so poignant. With the empire's gradual fragmentation, the large-scale, state-sponsored building projects that required this advanced material ceased. Specialized knowledge of the master mixers, once passed down through guilds and large engineering corps, became fragmented and then faded. The recipe was not stolen or destroyed in a single catastrophe. It simply slipped away through disuse, a victim of changing economic realities and the slow collapse of the systems that sustained such sophisticated craft. The story of Roman concrete is a powerful lesson in the ecology of knowledge. A technology, no matter how brilliant, does not exist in a vacuum. It depends on a living network of demand, training, resource supply, and shared purpose. When that network unravels, the knowledge can evaporate like water from a cracked basin. It asks us to look at our own technological wonders and consider what indispensable knowledge of ours might be just one generation of disinterest away from becoming another silent, beautiful mystery. While Roman concrete hardened into a monument of forgotten craft, another civilization was etching a different kind of legacy into far more fragile tablets. In the dust of ancient Mesopotamia, Babylonian astronomers kept a nightly vigil that would span centuries. Their canvas was wet clay, their pen a reed stylus, and their subject the entire visible cosmos. Night after night, for over 700 years, they recorded what they saw: the position of the moon against the fixed stars, the slow dance of the planets, the sudden, awe-inspiring darkness of an eclipse. These are the Babylonian astronomical diaries, and they are not a collection of myths or omens, though they were used for those purposes. They are a raw, running logbook of the sky, one of the most astonishing feats of long-term data collection in human history. Imagine the discipline required. Generation after generation of scribes, trained in the same meticulous system, looking up and writing down, regardless of war, famine, or the rise and fall of kings. The sky was their constant, and they became its faithful secretaries. This relentless accumulation of data allowed them to do something revolutionary. They moved from simply observing patterns to predicting them mathematically. By comparing centuries of eclipse records, they identified the Saros cycle, a period of approximately 18 years and 11 days after which the Sun, Earth, and Moon returned to nearly the same relative geometry, producing a similar eclipse. This meant they could forecast these terrifying celestial events not as divine whims, but as calculable phenomena. Their motivation was deeply practical, rooted in the needs of their society. Precise astronomy was essential for maintaining an accurate calendar to schedule planting and religious festivals. It was the engine of their astrology, the belief that celestial movements influenced earthly affairs, a system used to guide kings and reassure the public. Yet the method they developed to serve these ends was rigorously empirical and quantitative. They developed complex arithmetical schemes, step-by-step functions that could model the varying speeds of the moon and planets, essentially creating early mathematical software run not on silicon, but in the minds of their scholars. So how did they achieve such precision with nothing but the naked eye? Their tools were simple but masterfully used. They employed a basic unit of measurement, the finger, roughly equivalent to 1/4 of a degree. They used a viewing tube called to steady their gaze and make consistent measurements against a fixed reference frame, often the horizon or specific stars. The real instrument, however, was their unwavering patience and their commitment to a shared, standardized system of notation. This transforms our understanding of scientific origins. Here, over a millennium before the great Greek philosophers, we see the core of the scientific method in action, systematic observation leading to the recognition of patterns, which then fuels the creation of testable predictive models. The Babylonian diaries represent a different path to knowledge than the philosophical deduction of the Greeks. It was a bottom-up, data-driven approach. Their work provided the essential raw numbers that later astronomers, from Hipparchus to Ptolemy, would use to build their own cosmic models. This centuries-long project asks a profound question of our modern, fast-paced world. In an age of instant digital data, have we lost the vital virtue of patient, generational observation? The Babylonians teach us that some truths about the universe are not revealed in a flash of insight, but in the slow, steady accumulation of tiny marks on a clay tablet, a testament to the belief that if you watch the sky long enough and carefully enough, it will eventually whisper its secrets. Centuries of patient skywatching gave us the rhythm of the heavens, but what about the sudden, unpredictable shudder of the earth beneath our feet? In the year 132, in the court of the Han dynasty, the scholar unveiled an object of profound elegance and purpose. It stood as a bronze vessel, perhaps as tall as a man, adorned around its circumference with 8 dragon heads. Each dragon clutched a bronze ball in its jaws, and below each, a corresponding bronze frog sat with its mouth open, waiting. This was the Yi, an instrument for inquiring into the wind and the movement of the earth, and it was the world's first. Its operation was a spectacle of mechanical intuition. When a distant earthquake sent its tremors racing through the ground, an ingenious mechanism hidden inside the vessel would be triggered. A single dragon, facing the direction from which the seismic waves arrived, would release its ball. The ball would clatter into the mouth of the frog below with a resonant chime, audibly and visually announcing both the occurrence of the quake and its approximate direction, even from hundreds of miles away. The historical records are clear: the device worked. On one occasion, it indicated a quake to the west when no local tremor was felt. Days later, a messenger arrived from a distant commandery reporting a major earthquake, confirming the instrument's remote sensing ability. The exact internal mechanism, lost to time, is a subject of lively scholarly debate. Some modern reconstructions suggest a simple but clever pendulum at the vessel's heart. A heavy mass, delicately suspended, would remain inert until the specific angle of arriving seismic waves set it swinging, triggering a lever that opened only the dragon's mouth aligned with the disturbance. Others propose a system of inverted balanced levers that would tip in response to ground motion. Regardless of the precise engineering, the principle is what matters. Understood that the energy of an earthquake travels in waves, and that those waves have a direction that can be detected and indicated by a mechanical device. This was not mystical prognostication, it was instrumental geophysics. The invention served a deeply practical need for a vast, centralized empire. Quick knowledge of a distant earthquake was critical for the imperial administration. It allowed for the rapid dispatch of aid, the assessment of damage to infrastructure and agriculture, and the management of reports from regional governors. In a very real sense, this bronze vessel was an early warning system, turning an invisible terrestrial force into actionable administrative data. It represents a monumental leap in thinking, moving from experiencing natural disasters as chaotic acts of fate to treating them as measurable physical phenomena that could be systematically observed and reported. asks us to reconsider the timeline of discovery. It shows that the desire to build machines that extend our senses into the invisible realms of nature is an ancient and cross-cultural drive. Long before the modern seismograph with its rolling paper drum, a Han Dynasty polymath had already grasped the essential idea that the Earth speaks in tremors, and we can build a listener. A listener for the Earth's tremors required precision, but ambition on a truly monumental scale demanded something else entirely. Deep in the humid lowlands of what is now Mexico, the Olmec civilization left behind a gallery of stone giants. These are the colossal heads, each one a single towering portrait carved from a block of volcanic basalt, some weighing as much as 50 tons. Their faces are serene yet imposing, wearing distinctive helmet-like headgear, their features individual and unmistakably human. They were not assembled, but liberated from the mountain, each one from a single boulder, and then moved somehow across dozens of miles of swampy jungle and rolling terrain to their final sacred sites. This presents one of antiquity's most gripping logistical puzzles. The Olmec had no wheels, no metal tools harder than the stone they worked, and no domesticated animals like oxen or horses to pull such masses. So how did they do it? The answer is a testament to human ingenuity and collective will. Researchers believe the process began with an intimate knowledge of local geology, identifying the perfect basalt boulders in the mountains. Using harder stone hammers and water to fracture and shape the rock, teams of artisans would have rough carved the visage right at the quarry site, lightening the load before the journey began. Then came the epic move. The most likely method involved a combination of sledges, wooden rollers, and levers. Teams would have laid a track of lubricated logs, painstakingly inching the ton head forward as rollers were moved from the back to the front. For river crossings or coastal transport, they may have lashed the heads to giant balsa wood rafts, using the water's buoyancy to do the heavy lifting. Every step of this operation was a live physics experiment. It required a deep, practical understanding of friction, leverage, center of gravity, and the limits of materials. They learned through trial and error how many ropes were needed, how to secure the load, how to navigate slopes without losing control. This was not abstract science, it was science written in sweat and coordinated motion. The investment is staggering to consider. The labor was not for a defensive wall or an irrigation canal, but for a portrait. This tells us the Olmec's priorities were woven with spiritual and political threads. These heads are thought to represent powerful rulers or revered ancestors, their permanent watch over the community serving to legitimize authority and unify identity. The ability to command such a project demonstrated a ruler's power, while the communal effort of moving the stone likely bonded the society together in a shared monumental achievement. The heads, therefore, are far more than art. They are the physical proof of a society that had mastered the art of the possible. They had solved the equation of mass times distance through organization, turning a mountain's heart into a symbol of their collective vision. They make us wonder, what are the modern monuments we choose to build, and what do the immense efforts we pour into them say about what we truly value? The immense stone heads of the Olmec were a testament to collective will and practical physics. But in another ancient culture, the pursuit of precision turned inward, toward the realm of pure number and form. Within the sacred texts of ancient India, a tradition of thought was being preserved that would quietly shape the foundations of mathematics itself. The sutras, composed as appendices to the Vedas between roughly 800 and 500 years before the Common Era, are not philosophical treatises in the way we might expect. They are practical manuals, filled with geometric rules for the exact construction of the brick fire altars used in Vedic rituals. Their purpose was deeply spiritual, to ensure the correct proportions for ceremonies believed to maintain cosmic order. Yet within these instructions for priests, we find a startlingly abstract and sophisticated mathematical mind at work. The texts demonstrate a clear, practical understanding of the relationship between the sides of a right-angled triangle, the principle we know as the Pythagorean theorem. They provide methods for constructing a square equal in area to a given rectangle, or for doubling the area of a square, operations that require grappling with irrational numbers like the square root of 2. They even present early algebraic principles, solving equations to find unknown lengths. This knowledge was not merely observed, it was proven through geometric reasoning, a sequence of logical steps that established universal truths. Here was mathematics developed not for trade or engineering, but for the perfection of a sacred act. The altar's shape, its area, its symmetry, all had to be flawless to please the gods. This ritual demand for absolute accuracy became a powerful engine for discovery. It forced priests to think in terms of general rules and proofs, moving beyond specific measurements to universal principles. How does a circle relate to a square of equal area? How can you transform one complex shape into another without losing a single unit of sacred space? These were the puzzles that drove their inquiry. The sutras are also a bridge between oral and written knowledge. They represent the codification of a much older oral tradition, where complex geometric and numerical relationships were memorized and passed down through generations of teachers and students. By committing these rules to text, they preserved a system of reasoning that might otherwise have been lost. This tradition shatters the notion of a single, linear origin for scientific thought. It shows that the same fundamental mathematical concepts can emerge independently from vastly different cultural soil. In this case, one deeply rooted in ceremony and cosmic harmony. The Vedic mathematicians were not doing science as we define it today, but they were engaging in a form of rigorous, abstract thinking that is the very essence of the scientific spirit. Their work whispers a profound question across the centuries: how many other seeds of discovery have been sown not in laboratories or marketplaces, but in the quiet, meticulous spaces of ritual, where the human desire for perfection meets the timeless language of geometry, that profound grasp of geometry and number finds its ultimate expression not in space, but in time itself. For the Maya, time was not a simple river flowing from past to future. It was a living, breathing entity, woven from multiple, interlocking cycles that governed everything from the harvest to the fate of kings. To navigate this complex cosmos, they engineered a masterpiece of intellectual architecture, a calendar system of staggering sophistication. At its heart were two primary gears, constantly turning in relation to each other. The first was the N, a 260-day sacred cycle. This was not based on any obvious astronomical phenomenon, but was deeply woven into ritual and divination, with each day carrying a unique spiritual energy defined by the combination of a number and a named deity. The second was a 365-day solar year, divided into 18 months of 20 days, plus a short, unlucky period of 5 days at the end. When you interlock these two cycles, a fascinating pattern emerges. It takes exactly 18,980 days, or roughly 52 solar years, for any specific combination of an end date and a date to repeat. This grand cycle is known as the calendar round. For the Maya, this 52-year period was a complete era, a bundle of time whose completion was met with solemn ceremony and the renewal of temples and hearths. But to record history across generations, they needed something more. This is where their true genius shines, in the long count. This was a linear count of days from a mythical starting point. A day zero they calculated as August 11th, 3,114 years before the Common Era. They counted in a modified base 20 system, with units representing days, then 20-day months, then 360-day years, and so on, ascending through cycles that could stretch for millions of years into the past or future. To perform these vast calculations, they required a crucial conceptual tool, the concept of zero. They developed a shell-like symbol to represent the absence of a quantity, a placeholder that made their positional notation system work with flawless precision, an idea that would not appear in Europe for nearly another millennium. Their astronomical observations, preserved in precious bark paper codices, were breathtakingly accurate. Using nothing but the naked eye and carefully aligned architectural, they calculated the solar year to be more precise than the Julian calendar used in Europe at the time. They tracked the complex cycles of Venus with extraordinary detail, knowing its appearance as the morning or evening star over a 584-day period, and they could predict solar eclipses. This was not abstract stargazing. It was a practical science of time, essential for knowing when to plant maize, when to conduct ceremonies to ensure rain, and when to schedule the coronations and wars of rulers whose legitimacy was tied to celestial harmony. Their view of time was profoundly cyclical, yet meticulously recorded. They believed history repeated itself, that the gods reenacted cosmic dramas on corresponding dates across vast cycles. This created a unique sense of causality, where past events were not just lessons, but active templates for the present. A king might go to war on a specific date because an ancestor had triumphed on that same calendar position centuries before, harnessing the same favorable cosmic energy. The Mayan calendar system, therefore, is far more than a way to mark days. It is a comprehensive model of reality, a fusion of precise observation, advanced mathematics, and deep cosmology. It represents a pinnacle of indigenous scientific thought, proving that the human drive to measure, predict, and find meaning in the cycles of existence is a universal and profoundly creative force. A perfect calendar could predict the rains, but lifting that water to the fields was another matter entirely. In the 3rd century before the Common Era, a Greek inventor in the city of tackled this universal problem with a shape of elegant simplicity. Archimedes is said to have designed a device that is breathtaking in its logic, a wide screw, a helix, turning inside a hollow cylinder. When one end is placed in a water source and the assembly is rotated, the spiral chambers scoop the liquid, lifting it steadily upward along the incline until it pours out the top. This is the Archimedes Screw, a machine that transformed the relationship between land and water. Its genius lies in a profound conceptual leap, applying the principle of the inclined plane, one of the basic simple machines, to the behavior of a fluid. Instead of rolling a heavy object up a ramp, the ramp itself rotates, carrying the water along its gentle, spiraling path. The design is remarkably forgiving. It does not require tightly fitted pistons or delicate valves. It can handle water thick with silt and debris without clogging. It is powered by human or animal labor, turning a crank, or even by the flow of a river itself. And it is incredibly durable, built from wood or metal, with no complex parts to fail. For over 2,000 years, its form has seen almost no fundamental change, a testament to the timelessness of a truly efficient solution. From the vineyards of the Mediterranean to the rice paddies of ancient China, where similar devices appeared independently, the screw became a cornerstone of agricultural life. It drained swampy land for settlement, lifted water from rivers into irrigation canals, and even emptied the bilges of ships. In some forms, it is still used today in treatment plants and certain gentle industrial processes. The screw's endurance answers a deeper question about the nature of invention. It was not a lucky accident, but technology born from theoretical insight meeting a stark practical need. Archimedes was a geometer and a physicist, a man who understood the mathematics of curves and the mechanics of leverage. He did not just build a tool, he engineered a principle. This device shows how a deep understanding of abstract geometry could be directed toward the most fundamental civic challenges, feeding cities and reclaiming land. It represents a moment where pure thought rolled up its sleeves and went to work. Why has this design persisted while so many others were forgotten? Because it speaks a universal language of efficiency. It solves a problem with minimal complexity, maximum reliability, and graceful adaptability. In its endless, rising turn, we see the perfect marriage of mind and material, a spiral of ingenuity that has lifted civilizations for. Far from the vast libraries of the mainland, on the most isolated inhabited island on Earth, another silent language waits. Carved into weathered wooden tablets known to the world as Easter Island, the glyphs present a puzzle born of profound solitude. The symbols themselves are a gallery of the island's closed world, featuring frigate birds and tuna fish, palm trees, and strange geometric figures, all etched with a rhythmic, artistic hand. Their arrangement is uniquely methodical, written in a pattern called boustrophedon, where one line reads left to right and the next right to left, as if the hand were plowing a field, turning at each furrow. This is not random scratching. It is a deliberate, structured system, yet one that remains stubbornly mute to outside understanding. The mere existence of on such a remote island is a historical shockwave. It forces a difficult question onto the stage. Was this a completely independent invention of writing, a stunning intellectual spark that ignited in total isolation? Or does it whisper of a forgotten connection, a thread of contact with other Polynesian voyagers or even South American cultures that has since vanished from memory? Either answer is revolutionary. Independent invention would place, among the very few cradles of writing in human history, appear to ancient Mesopotamia or China. A lost connection suggests a web of Pacific knowledge far more extensive than our current maps can show. The content of the tablets, if we could ever read it, would be a treasure beyond price. It would not be a king's boast or a merchant's ledger. In this fragile ecosystem, where every plant and animal held the key to survival, the glyphs likely recorded the vital knowledge of a people. They may have been sacred chants invoking the birdman god, genealogies tracing lineage back to the legendary founder, or precise astronomical charts for navigating the featureless ocean or timing the seasonal tuna runs. They could be a codex of ecological wisdom, noting the blooming cycles of the extinct palm or the nesting grounds of seabirds. Each tablet is a potential encyclopedia of a lost world, a direct line into the mind, their history, their fears, and their understanding of the cosmos they inhabited. Like the manuscript, is a closed cognitive system. It represents a way of organizing thought that flourished, was used by a community of speakers and readers, and then was sealed shut by the harsh tides of history, likely after European contact and the tragic societal changes that followed. The last individuals who could interpret these glyphs passed on, taking the key with them. Our struggle to decipher it now is about more than solving a code. It is an exercise in profound humility, forcing us to confront the sheer diversity of human cognition. It demonstrates that there are ways of structuring knowledge, of linking symbol to meaning, that are entirely foreign to our own alphabetical or logographic traditions. The very logic of the script might be built on metaphors, rhythms, or spatial relationships we have not yet thought to look for. This silent wood holds a poignant, universal lesson, is a stark monument to the fragility of intellectual light. It shows us that a system of knowledge, no matter how coherent and vital to its creators, is not a permanent fixture. It is a flame that requires a community to tend it, to pass it from hand to hand and mind to mind. When that chain is broken, the flame gutters and dies, leaving behind only the beautiful, cryptic smoke patterns it etched into the ceiling of history. The glyphs stand as a quiet warning and a deep mystery, asking us what brilliant, unique ways of seeing the world have already flickered out, leaving no one to remember the tune they were meant to sing. The silent glyphs represent a lost system of meaning, but one symbol born from emptiness would go on to conquer the world of thought. Across civilizations, the void presented a stubborn problem. Ancient Babylonian astronomers needed a way to distinguish 61 from 601 in their clay tablets, so they used a simple placeholder, a pair of angled wedges, to mark an empty column. It was a practical notation, a space holder, but it was not yet a number you could calculate with. That profound leap would occur centuries later in the vibrant intellectual climate of India. By the 5th century, Indian mathematicians were not just using a dot or a small circle to represent an empty place. They were beginning to treat it as a legitimate entity in its own right. They called it, meaning void or emptiness, a concept with deep roots in philosophical and spiritual traditions contemplating the nature of reality. Then, in the 7th century, the mathematician performed a staggering act of abstract courage. He wrote down formal rules for arithmetic with zero. He declared that a number added to zero remains the same, that a number subtracted from zero becomes negative, and he wrestled with the perplexing results of dividing by zero. This was the moment zero transformed from a mere placeholder into a full-fledged number, a citizen in the Republic of Mathematics. This was not just an innovation, it was a revolution in cognition. To understand why, consider trying to do long division with Roman numerals. The system lacks a place value, making complex calculation a torturous ordeal of abacus and mental gymnastics. With a positional system including zero, numbers became a dynamic, efficient language. The zero acted as a pivot, allowing digits to shift in value based on their place, turning arithmetic from a craft into a scalable science. This tool supercharged every field it touched. Algebra flourished, as equations could now be balanced and solved with a clarity previously impossible. Astronomers could calculate more precise planetary positions. The concept would travel along trade routes, carried by scholars like the Persian Al into the Islamic world and eventually to Europe. Yet its adoption was not swift or easy. For many medieval European thinkers, steeped in Aristotelian philosophy that rejected the void, zero was a dangerous, almost heretical idea. How could nothing be something? It represented chaos, the void, a troubling gap in the ordered universe. Its very name, from the Arabic, would evolve into our words zero and cipher, terms still carrying a hint of hidden code and mystery. The resistance highlights a timeless truth about scientific progress. The greatest barriers are often not technical, but conceptual. Embracing zero required a fundamental shift in worldview, an acceptance that a symbol for absence could be the most powerful presence in a logical system. Its ultimate triumph laid the invisible foundation for our digital age. The binary code that powers every computer, every stream of light on this screen, is a direct descendant of that Indian insight. It is a universe built entirely on two symbols, one and zero, being and being, the fundamental duality made possible by giving nothingness a name and a function. The journey of zero, from a blank space in a Babylonian ledger to the bedrock of global technology, underscores the most profound theme of our entire exploration. The origins of scientific thinking are not merely a collection of gadgets and observations. They are a story of the human mind learning to embrace the counterintuitive, to give form to the formless, and to discover that sometimes the most powerful force for understanding everything begins with the courage to conceive of nothing. From the void of zero to the whirling sphere of steam, these 25 fragments form a single, undeniable portrait. The ancient drive to know was not a single flame lit in Greece, but a constellation of sparks igniting across the globe, each burning with its own color and purpose. This journey reveals a science that was, above all else, profoundly human. It was woven into the fabric of daily survival and sacred duty. The precision of the Babylonian astronomer served his king and his gods. The geometry of the Vedic priest ensured a ritual's cosmic power. The metallurgy of the Gupta smith produced a pillar that would defy time itself, a testament to both devotion and durability. Necessity was the universal catalyst, whether it was the need to predict the Nile's flood, to lift water to a parched field, to heal a broken limb, or to chart a course across a trackless sea. These were not abstract puzzles for a privileged few. They were urgent questions asked by entire cultures and answered through generations of collective effort. We see this in the anonymous teams who moved the Olmec heads, in the scribes who kept the celestial diaries for 700 years, and in the guilds who perfected the Roman concrete recipe. The genius was often cumulative, not solitary. This global tapestry directly challenges a long-held story, the idea of a Greek miracle that alone gave birth to rational thought. Our journey shows that while the Greeks made monumental contributions to systematizing knowledge, they were participants in a much older, wider conversation. The Babylonians provided the data, the Indians the mathematics, the Chinese the instrumental ingenuity, and countless others the practical engineering. The foundations of science are not the property of one civilization, but the shared inheritance of humanity, built from countless hands and minds observing their own corner of the world and daring to find a pattern within it. At its heart, across every discovery, we find the same basic cycle, a human universal. It begins with observation, watching the stars or feeling the strange tingle from a wet metal jar. This leads to a hypothesis, an intuitive guess that perhaps these events are connected or can be controlled. Then comes a form of experimentation, from the deliberate trial and error at the forge to the calculated construction of a scale model. Finally, there is model building, whether it is a bronze cosmos, a calendar of interlocking cycles, or a map synthesizing a dozen sources into a new vision of the world. This process is not modern, it is innate. And this leads us to the most haunting lesson of all, the profound fragility of knowledge. The mechanism sank on a single voyage. The Library of Alexandria faded over centuries of neglect and conflict. The meaning of the disc and the glyphs vanished when the last speaker passed. Societies transition, priorities shift, and the delicate chain of transmission from master to apprentice can break, leaving behind only the silent artifact, a question without its answer. This history of loss casts our own era in a stark new light. We live in an age of seemingly permanent digital records, yet we face our own forms of fragility, from data corruption to shifting technological formats. What is our responsibility to the fragments we have recovered and to the knowledge we are creating now? How do we ensure that the insights of our time, like the whispers from these ancient objects, are not just preserved, but remain understandable and meaningful to those who come after us? This is the quiet challenge these discoveries leave with us, a call to become not just consumers of history, but active stewards of the long, ongoing human conversation with the universe. The intricate gears of the mechanism and the abstract power of zero are not endpoints, but waypoints in a much longer story. They are fragments of a global mosaic, testaments to a universal impulse. For thousands of years, across every inhabited continent, people looked at the stars, felt the earth tremble, and wondered why. They did not have our laboratories or our terminology, but they possessed the same essential toolkit, curiosity, patience, and a profound need to make sense of their surroundings. These 25 discoveries are not just ancient artifacts, they are the physical echoes of that timeless conversation between humanity and the mysteries of the universe. They prove that the scientific spirit is not a product of any single era or culture, but a fundamental thread woven into the very fabric of our shared history. This long legacy shows us that science, at its heart, is not a collection of facts, but a method. It is the courage to observe carefully, to ask a difficult question, to test an idea through trial and error, and to build a model, whether in clay, bronze, or thought, that explains a little more of the world. From the Babylonian astronomer tracking Venus to the Olmec engineer moving a stone giant, the same cycle of inquiry repeats, dressed in different clothes but driven by the same relentless human drive. As we navigate our own era of complex challenges, from environmental shifts to technological frontiers, we stand on the shoulders of all these anonymous observers and ingenious tinkerers. Their legacy is not just the specific knowledge they uncovered, but the example they set, a testament to ingenuity and quiet perseverance in the face of the unknown. Their stories remind us that progress is often slow, fragile, and built collaboratively across generations. We are the current custodians of this long conversation. I would love to hear which of these discoveries resonated most with you. Was it the computational genius of the device, the haunting silence of the manuscript, or the practical geometry of the lines? Share your thoughts in the comments below, and if you know of another ancient marvel that reveals early scientific thinking, please tell us about it. If you enjoyed this journey into the deep origins of our quest to understand, please subscribe for more explorations into the mysteries of our past. Thank you for joining me on this voyage through time. Keep observing, keep questioning, and never stop wondering about the incredible story of how we came to know our